short chat that we have today is to give you an overview of what we do at CERN. So I don't know what's the level, the physics level that you have, but I'll give you really a very public-oriented, general public-oriented overview of what we do at CERN, and in case we can also go through some technical details if you have any question. So the presentation will be around 45 minutes, and then I'll also leave some time for questions, but feel free also to ask questions during the presentation. If it's something that is related to the slide I'm on, I can stop and make the argument more clear, answer your questions. Otherwise, we can move everything to the end. And there is also, we ask you to fill a survey at the end of the presentation on the page where you have the link to connect to the Zoom conference, and then you can find my slides, so you can download the slide I'm showing you. This is because I put also some link inside my slides, so it would be very interesting also to go through additional materials. At the end of the page, below the link to connect to the conference, you can also find a survey. And we ask you to fill a survey just to get feedback about this kind of conferences. So a few words about me. I'm a particle physicist that is working with the Adams experiment. I'm looking for physics beyond the standard model, generically on long-wave particles that are particles that can be produced by the collision of protons inside the detector, travel a certain path across the detector, and then decay, transform into different kind of particles. These are particles that are predicted by many theories, and many theorists think that these particles belong to what is called the dark hidden sector of the universe. On the same topic, I'm also working for a proposal for a new experiment that, if approved, will be installed on the surface above the CMS detector. This will be a very big detector, 1 nanometer times 1 nanometer, and will be used to study very long-wave particles. So particles that are produced by the collision of protons but travel a much longer path, like 100 meters, and then they got undetected by the detector that are on the ground, like other CMS and so on. As a detector on the surface, it can also be used to study cosmic rays. That is a free source of particles. That it was actually the first way we used to study particles, because in the 1920s, 30s, we didn't have any accelerator to systematically produce particles in the laboratory. So the only way of studying particles was really producing a detector, taking this detector, put this detector in the balloons that were going up in the atmosphere, and they were looking for this kind of particle. Then we invented the accelerator so that we can systematically produce particles in the laboratories. Okay, so just a few words about CERN. CERN is an international organization. It was founded in 1953. Actually, the first one it was founded was a council. So the acronym is European Council for Nuclear Research. And this is a picture of the first council that was taken where the future of CERN, the policy of CERN, and so on was decided. After here, in 1954, this council became an organization, like basically, say, the United Nations. I see there was a message about sound is low. Is it okay for everyone? Just to understand if it's my problem or not.
I think the sound is okay, but little bit echo maybe is coming.
Okay. So yeah, so it's an organization basically like the United Nations, and they kept the same acronym CERN, despite the fact that it changed the concept from organization. This is 1954, and this is one of the famous pictures that was taken the day the construction of the CERN site started. So this is the countryside of Geneva, where now you have a laboratory and offices of CERN, where this is really the day where we see the work for the construction of the site started. So CERN is an international organization. It has 23 member states. They are mostly European, but not only European. You can see, for example, it's also India. And these 23 member states provide CERN with a annual budget that for the 2020 was 1.2 billion Swiss francs. And this is more or less equivalent to one cappuccino per European citizen per year. Then CERN can use this budget to pay, for example, the construction of a new building, accelerator, detector, to pay the personnel, salary, to pay also the electricity bill and the different bills that you have at CERN. So, but at CERN we don't have only 23 member states. It's really more a world collaboration. So we have member states that provide a annual budget, but also non-member states, like, for example, as you can see, the United States. The United States do not provide CERN with an annual budget, but that doesn't mean they do not contribute to the research at CERN, because all these non-member states have many laboratories that are funded directly by the government. These laboratories have workshop engineers, technicians, physicists, and they can contribute the development and construction of the detector at CERN. But we have this very big detector like Atlas and CMS. Not all the components are built at CERN. Most of the time, you have all the different components that are built by different companies, by different country, different research institute, and then everything is shipped to CERN and assembled directly at CERN. So you see that the world is very well covered. So we have many countries that are working in this collaboration at CERN. It's very nice. So CERN is basically a small town. We have 20,000 people that are working at CERN. That doesn't mean they are physically all present at CERN. During normal time, we have 8,000 people working on the CERN site. This time, we have around 4,000, a little bit more people working on the CERN site. This is how they are distributed. So we have 2,600 members of staff. This is CERN personnel, so people paid directly by CERN. These are physicists, engineers, technicians, and so on. We have fellows, apprentices, or sort of postdoc. We have students, and I also have a slide to mention the different opportunities for students. We have external companies. These are like contractors that come from surrounding country, like France, Switzerland, Italy, Germany, and they come to CERN to do some work. Like, for example, when you need to build do some refurbishment of the building or do some excavation for power and so on, everything is done by external companies. And then we have the users. What are the users? The users are the vast majority of people working at CERN. These are not, this is not directly CERN personnel. These are persons that maybe are working for some university in the States and so on, that maybe they spend most of the time in the university because they need to do some also some teaching, but they also do some work at CERN. So they might come to CERN for some period of time. They might be fully based at CERN, depending on the contract. This is how they are. So you see many people. So it's a small town. We have fire brigade, travel office, medical center, bank, kindergarten, and also in order to host the user and to host also the student on the campus. So, okay, now moving to more the physics part. So there are many open questions, and I try to summarize what are the main ones that really need to have be investigated. So I tried this slide to summarize, let's say, the hot topic of the moment. Certainly, a very hot topic is dark matter. So what is dark matter? Well, we don't know yet exactly what it's made of. But what we know that most of the matter that made the universe is made of something that we still don't know. So when we look at the universe with a telescope or a radio telescope, what you see is only 5% of the matter that made the universe. It's only 5%. So the stars, the galaxies that we see, it's only 5% of the matter. The rest of 95% of the rest is still not clear what it is. We know that more or less 27% is made of dark matter, and the rest is dark energy. But what is dark matter made of? Well, it's still not clear. There are many theories, but we still don't know what exactly this dark matter is made of. But why we know that dark matter exists? Well, The dark matter is called dark because it does not emit any light, any radio signal. So we cannot really see it directly with telescope or radio telescope. But then why we know that the dark matter exists? Well, because the dark matter does not emit light or radio signal, but it has a mass. So it generates gravity. Right? So imagine like the solar system where you have the sun with all the planets going around, and everything is driven by the dynamics, powered by the gravitational force between the different cores. Well, the same happened in the galaxy. So all the galaxies, like our Milky Way, they are not static. Right? They rotate. Okay. Now, if you look at the rotation speed of the galaxy, what you find is that the galaxy is rotating at a speed that is much higher than what we expect looking at the visible mass. So we can only assume that there is additional mass that make this galaxy rotating faster than what we expect. And this is why we call this dark matter. Another thing is the matter-antimatter asymmetry. Now, antimatter is different from dark matter. Dark matter is completely new particle, while antimatter is a standard particle. So proton, antiproton, electron, anti-electron. So when the antimatter was discovered, they thought it was simply a specular copy of the matter. So proton and antiproton are exactly the same particle. They just have an opposite charge. Around 60 years ago, they found that this is not true completely. I mean, the matter and antimatter behave in a slightly different way. So there is an asymmetry. And this asymmetry might explain why our universe is, as far as we know, completely dominated by matter. So when you look at the universe, you see planets, galaxies, stars made of matter, but nothing made of antimatter. Right? Antimatter should be produced at the beginning of the universe. So at a certain point, antimatter disappears completely from the universe, and it's still not clear the process that made that. Another thing is the mass of the neutrinos. The neutrinos, we know they have a mass for sure, but we still don't know what is the value of the mass. We haven't managed to measure the mass of the neutrino yet. So the neutrino is a very complicated particle. It's very complicated to measure the properties of the neutrinos. And in fact, we still don't know what is the mass. And of course, also the origin of the universe. The first fraction of a second right after the Big Bang, how the universe evolved, it is still really unclear. But let's start from what we know. So this is very briefly the standard model, what we call the standard model of particle physics. These are the fundamental particles that we know at the moment. So you see, there are not so many. There are two big families, what we call the quarks, and there are 6, and what we call the leptons, and again, there are 6. Why 6 quarks and 6 leptons? Well, it's still not completely clear why not more than 6 in principle. Well, in principle we can have, but from observation we know that there are not more than 6 quarks and 6 leptons. But when you look at the universe, the galaxy, the stars, they are only made of these 4 particles, because the standard matter, stable matter that surrounds us, is made of protons and neutrons. And the proton and neutrons are made of a combination both up and down. This one. And plus you have this cloud of electrons that surround the nucleus. So the stable matter that we see when we take a telescope is only made of these 4 particles. This additional particle can be produced in cosmic ray interaction and of course in the accelerators. So 6 quarks, 6 leptons, and then we have 4 fundamental forces in nature. We have the gravity, that we know very well. We have the strong force. The strong force is the force that keep together the quarks inside the protons and neutrons. We have the electromagnetic force. Take 2 particles like protons at the same charge, so they repel. Opposite charge attract. So this is the electrostatic electromagnetic force. And then we have the weak force that is responsible for some nuclear decay. All these forces have one or more what we call mediators, that are the gauge bosons. These are sort of messengers that transport information about the force. Come back to the protons. The proton have an opposite form, so same charge, opposite the repel, right? But the closer the proton are, the higher is the repulsive force between the 2 protons. So there should be something that makes a sort of communication between the 2 protons that tells the proton that they are closer and closer and closer. So the force is stronger and stronger and stronger. In the case of electromagnetic force, the communicator, the mediator, is the photons. The photon is the mediator of the electromobility force. The gluons are the mediators of the strong force, the glue that keep together the quarks inside the protons and the neutrons. Then the W and Z boson are the mediator of the weak force, and also the gravity should also have a mediator that is called the graviton. But the graviton is not included in this scheme because from the theoretical point of view, the standard model cannot explain how the gravity behaves at particle level. But there are many theories in superconductor that predict the existence of gravitons, and we also have many social theories for gravitons. We haven't found it yet, but. And then the last, let's say, missing piece of the standard model was the Higgs that was discovered at CERN in 2012. That is the particle associated to what is called the Higgs field. Imagine like an additional force in the universe that explain why all the particles of the standard model have a certain mass. But why we need to go beyond the standard model? Why we need to look for new particles? Well, because, for example, none of these particles can explain dark matter. So if there is dark matter, it should be something completely new. But to look for new particles, we need the experiment. And at CERN, we have many experiments. We have a big experiment called the Four Giants one on the LHC that are happens in CMS, that are the two ones that is called the Higgs boson, as I recall. And we also have LHCb and Alice. So this is by the way, the view of the path of the LHC, that is 27 kilometers, is 100 meters underground. This is the Geneva Lake here, the Geneva city here, the Mont Blanc. But we don't have only 4 experiments. So we have many different kind of experiments that study many different type of, let's say, physics. Okay? We have experiments that study neutrinos. We have experiments that study the matter-antimatter asymmetry. We have a facility at CERN that is called AD, that is the anti-proton accelerator. And we have many where we produce anti-hydrogen, right? Anti-proton, anti-electron. And we have many experiments that go studies the properties of the anti-hydrogen. For example, the spectroscopy of the anti-hydrogen, or the effect of the gravity on the anti-hydrogen. Because it's clear, we know very well what is the effect of the gravity on the standard matter. And we don't know on the antimatter. We can assume it's the same, but it might be different, it might be higher, lower. So it's something that we don't know very well. So there are many experiments that study the property of the antimatter. There is an experiment that is not even at CERN. AMS is an experiment that was developed, assembled, and tested at CERN, but is installed on the ISS and is used to study cosmic rays, for example, for dark matter. There is also an experiment that studies the cloud. In this cloud chamber, we can reproduce the gas composition of the atmosphere, and sending particles, we can, for example, study what is the effect of the cosmic rays on the atmosphere, see how this evolve. That's an example. But to run an experiment, we need an accelerator. At CERN, we have many experiments, and we also have many accelerators. So an accelerator is a powerful machine that allows it to create new particles. Now, this is something that is very uncommon for normal life, because let's say daily life, if you take 2 apples and you smash 2 apples, you will certainly not get 2 bananas. That's clear. Well, this is something that happens in an accelerator, because you take particles like protons and you accelerate protons at the most speed of light. And when you smash these protons that are made of cut down gluons, you create completely new particles. Higgs boson, dark matter, electron, muon, whatever. This is thanks to the famous Einstein formula, the equivalence between the energy and the mass. So we transform in an accelerator energy to mass, and mass into energy, and we can start from certain particle like protons and produce completely new particles. So in this slide, I try to summarize what are the main components of a circular accelerator like LHC. Now, in a circular accelerator, you have a beam of particle in one direction, and another beam of particle going in the opposite direction. They are accelerated at the most speed of light, and they collide in 4 points where you have the experiment when 2 beams collide and you create new particles. So there are 3 main components in the accelerator. There is the accelerating cavity, that is the system that really accelerates the particle. It's based on a principle that is not so different from what happens to the surfer. Imagine the sort of a surf effect, right? If you have a surfer, right, that ride the C wave, and the C wave, and the surfer ride the wave, the same wave is pushing the surfer in the direction of the propagation of the wave, so in the direction of the beach, right? Well, you can imagine that the sea wave is an electromagnetic wave, and the surfer is our protons. So what we do inside this accelerating cavity, we generate an electromagnetic wave, a radio wave. There is a sort of antenna that generates a radio wave. Then the particle, proton, pass across the region where there is the electromagnetic wave, and like the surfer can ride, let's say, the wave, so it's pushing this electron, get the kick. Then the particle make a turn, pass inside the cavity, another kick, another kick. So every time the particle make a turn is accelerated. But this is a circular accelerator, so when you give a kick to the particle goes straight, right? So you need something that bend the trajectory of the particle so that the particle can make a circular trajectory. And this is the purpose of the second component, is the bending magnet. The bending magnet is not so different from the magnet that you have in the fridge. It's a simple dipole magnet with north and south poles, and it's based everything on the famous Lorentz force, the magnetic force. So you know that if you have a magnet, the magnet generates a magnetic field. When a charged particle enters inside the magnetic field, there is a force acting on the particle that bends the trajectory of the particle. So we don't have, of course, only 4 magnets. We have a series of magnets. Well, the blue pipe, when you Google LHC, you get this picture of these blue pipes. So these are the bending magnets. We have 1,232 of these 60-meter long blue pipe. And these are the bending magnets that bend the trajectory of the particle inside the accelerator. Then the third component is what we call the focusing magnet. Instead of having 2 poles, these have 4 poles, 2 north and 2 south poles. So it's a quadruple magnet. And this focusing magnet works exactly like a focusing lens. Imagine focusing lens, you have a lens here, you have a ray of light. When the ray of light crosses the lens, is bent and focused, concentrated in one point. We do the same, so something similar also with the protons. So why we need to focus the protons? Well, because inside the accelerator, we don't have a single proton going around in one direction and another one in the opposite direction. We have bunches of protons, bunches made of several protons, thousands of protons, billions of protons. Now, what happened? These bunches have more or less a length of 30 centimeters with a minimum width of 20 microns, and they contain 100 billion of protons. So 100 billion of particles with the same charge. So what happened to the particles with the same charge? They repel. Right? So if you inject this beam inside the accelerator, the particles start repelling, and so the beam starts spreading away, so the particles start flying away. You need to keep all these beams squeezed, okay? These particles squeezed inside the magnets. That's the purpose of the focusing magnets. Okay? So as I already anticipated at CERN, we have many accelerators. We have the LHC, 7 kilometers. And we have different kinds of accelerator. We have the SPS, 7 kilometers. Those are smaller accelerators. And the smaller accelerators are used to pre-accelerate the proton from the LHC, but also to provide proton to the different other experiments. Because I told you we have many experiments and they need protons. And you see that also these accelerators are very small, 157 meters circumference, 628 meters, but also very old. This is, for example, the oldest accelerator that we have, 1959. This is really the first circular accelerator that was built. If you want to have, for example, an idea of the path of the proton inside the accelerator, I'll post here a link to a nice video to show you the path inside the accelerator. But you can also go on Google Maps, and actually we had a street view at CERN on the surface, but also on the ground. So basically you can go and see the accelerators, so like walk inside the tunnel of the LHC, like the street view, and see also the detectors. So you also see, for example, CMS, and so on, in case you are curious. But where do we take the proton? Very briefly, well, we take, this is probably the simplest part of the process. We take the proton from the hydrogen gas. The hydrogen, you know, is made of proton and electron. So if you strip, you remove the electron, then you get only a plasma of protons. And this is what happened. We have a very small device that is called duoplasmatron that is a device like this, so it's very small, take the hydrogen gas with a certain rate and emit a a plasma of proton that then is inserted inside the accelerator and start the acceleration chain. Now, I just wanted to focus a little bit on the bending magnet, the blue pipe I mentioned before, because the magnet of the LHC are very special magnets. Right? Now, this is how they are made inside. So this is a picture of the tunnels that you can see with the also studio. So inside the magnet of the LHC, we have two pipes, right? Where you have one beam going in one direction and another beam going in the opposite direction. Now, around each pipe, you see on the left and the right, these are the magnets. These are not permanent magnets like the one that you have in the fridge, but these are electromagnets. What is generating a magnetic field? A current. If you take a piece of cable, okay, simple piece of cable, when you connect this cable to a power supply, when the current passes inside the cable, the electron that passes inside the cable generates a magnetic field. Then a magnet is made of several cables, and you cannot really see very well. But if you zoom really, you see that these magnets are made of several cables. Right? Each one carries a current, and each one generates a magnetic field that then is sum up and generate a desired magnetic field inside the pipe. But now, the magnetic field that you need to generate is proportional to the current. So the higher is the number of amps that pass inside the cables, the higher is the magnetic field generated. Now, to generate the magnetic field that we need at the LHC, we need to use around 13,000 amps. Now, just to give you an idea, in our house, we have around 13, 14 amps. So the current that we need in the accelerator is 1,000 times bigger than the one that we have usually in our house to power the fridge and the oven and so on. So, if you think at how you can carry this current, because I mean, at home we have 13, 14 amps, and we have a relatively small cables, right? But now, what happens if you take 13,000 amps and a small cable? It will melt immediately, because the copper that made the cable is a very good conductor, but it still has an electrical resistance. So when the current passes inside, it's like a sort of a friction, and this friction generates heat, right? And the heat is proportional to the current. So if you have a very big current, you have a lot of heat to use. So if you take a small cable, 30,000 amps, this cable will melt immediately. How you can carry all this current in a copper cable? Well, you need to increase the size. Now, to carry 30,000 amps in a single cable, you need a cable like this. But the magnet of the LHC are made of several cables. So that means that you need to use several cables like this. So you will end up with a gigantic, huge magnet that will certainly not fit inside the tunnel. So that's to say that it's impossible to build a magnet for the LHC using standard material like copper. What we do, we use a superconductor. A superconductor is a special material that in certain conditions has zero electrical resistance. So if you don't have electrical resistance, you don't have a Joule effect produced. So you don't have heat produced. So you can use a small cable and 13,000 amps because this cable will not produce heat. So the cable that you see here are made of an alloy of niobium titanium, that is the superconductor that we use for the LHC. The problem is that the superconductor is not superconductor at room temperature, but to have material being superconductor, you need to cool it down. And the one of the LHC need to be kept at minus 271 Celsius, so 1.9 Kelvin. So the LHC is a very powerful accelerator, but also a very powerful fridge. And we spend a very big amount of energy to power the accelerator, because consider that the energy consumption of the accelerator is equivalent to the one at the center of Geneva City. So it's 180 megawatts. If you want to have more details about superconductivity, also consider it here. But okay, let's move now to the detector, because you have taken this proton, you have accelerated this proton at almost the speed of light, and you cross this proton, and you create new particle. So what you need? Well, you need a very powerful camera that allows to measure the particle produced by the collision of protons. And these are the detectors that we have observed, like for example Atlas, you see here. And by the way, these are not a very small device, because just to give you an idea, this is a person compared to the size of Atlas. Atlas is 44 meters long, and 22 meters high for a weight of 7,000 tons. That is equivalent to the weight of the Eiffel Tower in Paris. It's a very big machine. And what we need to measure in a particle physics detector, we need to measure the fundamental properties of the particle. That means the trajectory of this particle. We need to measure the energy of this particle. We need to understand what is the charge of the particle, and also understand the kind of particle. Is an electron, is a muon, is a photon, so on. So to do that, we have different sub-detectors that allow to measure the different properties of the particle. Very close to the point where the proton collide, here we have what is called the tracking system. This is made of silicon detectors, similar to the sensor that say present in the camera, and they can precisely track the trajectory of all the particles produced by the collision of protons. Outside, which is in green and orange, these are the calorimeters. The calorimeters are the detectors that are used to measure the energy of the particle. How do they measure the energy? Well, they absorb the particle. The calorimeters are made of very dense material like lead and iron. By absorbing the particle, they can measure the energy. Actually, the calorimeter absorbs all the particles except for two. One is the neutrino matter. The neutrino is a very competitive particle to be measured. This is not something that we want to do at the LHC. And the other particle is the muon. The muon is a particle that is similar to the electron, but as a mass is much bigger than the electron, so the electron is absorbed by the calorimeter while the muon is scaled. That's why we need another detector that is the muon part, the muon detector here in blue that measure the muon particle. So tracking system to measure the trajectory, calorimeter to measure the energy, and the muon detector to measure the muon particle. How do we measure the charge? Well, we still use a magnetic field, because the magnetic force that I mentioned before depends on the speed of the particle, on the magnetic field, but also on the charge. So if you have a positive, you have a magnetic field, a positive particle is bent in one direction, a negative particle in the opposite direction. Neutral particle is straight. So if you generate a magnetic field in Atlas, in a detector, once you have reconstructed the trajectory of the particle, just look in which side the particle is bent or if it goes straight, you can understand what was the charge of the particle. And in Atlas, we have a solenoid that surrounds the tracking system, and the toroid, height of this coil that generate the torus, a sort of donuts that surround the calorimeter, to generate the magnetic field. If you want to have also more details about Atlas, I also post the link here. And this is a nice slice of Atlas to show you more details, the different detectors. So you have the tracking system, you have the calorimeter, the electromagnetic calorimeter, that measure the energy of electrons and photons, and the hadronic calorimeter, that measure the energy of the hadrons. The hadrons is a way of calling all the particles made of quarks. So the particles made of quarks are called hadrons. That's why at places a large hadron collider because they accelerate protons or nuclei, and that are made of proton neutrons. So it's a hadron. And then you have the muon electron. But when you collide protons many times per second, and you produce from this detector a lot of data. So you need a very powerful infrastructure that allows to process and analyze all the data that are produced by the collisions of protons. So this is what is called the LHC computing grid, that is a sort of cloud that connects CERN, that is the core, with our research institute university that are working with CERN. Imagine that each research institute or university have a small data center where we can have computers, so they have a CPU, they have a disk to save the data, and the CPU to analyze this data. If you sum up all these computers connected with the grid, we have around 1 million CPU cores. That is how a global supercomputer that is used to process and analyze all the data that are produced by the LHC. And if you want to have also more information about the grid, I also posted a link here, and I also posted here a link to a nice summary to show you, for example, from the data to discovery, how the data are processed at the LHC. But CERN is not only fundamental search, so you might imagine that all the technology that we developed for the accelerator, the detector, might have many applications in daily life. At CERN, we have a department that is called knowledge transfer. That's really this purpose, to make a sort of a link between the fundamental social goods and the external environment that we have. many applications, medical application, for example, adrenaline therapy reported here, treat the cancer using beam of particle that is much more efficient than the radiotherapy, for example, standard radiotherapy. We also have medical imaging. The web was another example, and humanitarian mission, not because we are sending physicists around, but the world in the Italian zone, but simply because we have a collaboration between CERN and UNOSAT, that is the United Nations satellite that can rapidly map the surface of the Earth. And this can be very, very important in case of disaster like earthquake, flooding, can really help analyzing the image from the satellite, thanks to some software that was developed at CERN, can help very quickly analyze the area affected by the disaster. So this is only some example. So recently there was also a task force against COVID, but we also share part of our computing power for the research standard. And as I said, I also have a slide about the program for students. We have many opportunities for students, I told you, and you can go on this site here and you see all the details about the different opportunities that we have for students. This is a picture of the summer student program that we could have last year and this year, but in the past year where students were coming to CERN for 2-3 months, and they were coming attending lecture where they talk about particle physics, detector, but also work on a small project. And this allows really to understand the work environment that we concern and understand better. Okay, so I will probably my screen. Okay, and the last slide is really to say thank you, but also to provide you with additional material. To provide you with additional material because in case you are interested, for example, I posted here a link about CERN open data. So we are gradually sharing the data that we are collecting at the LHC on the web. So basically, you can get all the data and you can basically discover the Higgs boson. So this is a real data collection that we can see. And information about history, about art at CERN, so that might be, and also event display. The image that you have in my title slide is not artistic. This is a real collision between particle and in a graphic way. We have many of these that really allow to understand, for example, when you collide bosons, you have production exposed by and so on. We have many of these that might be very interesting also for us, but for the public. And yeah, that's all I have. Thank you. And if you have any questions.
Yeah, dear student, if you have any question, please ask. And thanks for your nice presentation.
Thank you. You don't really need to use the chat. I mean, now you can also use directly the
Yes.
microphone if you want to use
I think you can ask a question directly.
Yeah. You don't really need to type in the chat. So,
Hello, sir. This is Saurabh.
Yeah.
So, is there any specific reason why do you call the gauge bosons as these vector bosons and the Higgs as scalar? I mean, why do you associate vector and scalar to these force carriers?
Why we call Higgs boson is a boson, right?
Yeah, the standard model part. Yes, at this slide.
Yeah, it is a boson. That's why we call it boson.
Yeah. So why do you associate scalar to that and vector to the gauge bosons? Any specific reason for that, for applying the vector thing to the gauge bosons? Like, why do we call it vector?
Because they are not scalar. No, sorry, I missed the question. Sorry.
I mean, there has to be some reason to be called vector bosons, and I was confused with these things, so I thought I will ask you about it.
Yeah, I mean there are different kind of
Yeah.
bosons that behave in a different. One is a scalar, and the other one is a vector. So that's
Yes.
why it's a scalar. You see that also the scalar, the Higgs has a spin 0.
Hello, sir. I also have a question. Can I ask, please?
Yes, yes, you can.
Yeah.
particles
I
also.
mean, if you change the Higgs field, everything's changed. So yeah, that's clear. So
Yes,
you might have many possibilities, infinite
yes,
possibilities. So
yes,
this is
yes,
what
yes.
yeah. So this is what we get. And
Mhm.
but yes, in principle, if the Higgs field was different, so that the mass of the quartz was of course different. And but in any case, we can we actually can because the big quark fly enough to be measured basically as a displaced vertex in the detector. So we have, for example, in the detector like a CMS, particular algorithm that are called big tagging that allow to really separate quark Z from quark like charm, so like quark. We can really, because we make a measurable trajectory inside the detector. Measure is still under microns, but it's something that we can measure in our detector. So it's something that we can measure. But yes, in any case, changing the Higgs field, there is still discussion about the.
Yes, yes.
There's still discussion about the Higgs mass. We are in a region of the stability, metastability, and instability. So that means that the Higgs the Higgs field is in a minimum or in a like a metastable state, and that means that at a certain point the Higgs can change the vacuum can change to go to the real minimum, and then everything in the universe change. So
yes, because the Higgs field, we don't know that means the current Higgs value is minimum or not. See, because it can be lower enough, means the lower state may be possible, means the up and down quark may be more stable. Quark may be possible if the Higgs field can be changed, and this maybe can lead to a new Big Bang, or those the new all the up and down quark maybe get changed into more low energy particles, and then maybe a new Big Bang created, and all the matter will be converted into those low mass particles, and the rest energy can be may become the others type of energy, etc., and can be there maybe another Big Bang possible.
Yeah, I honestly don't know what will happen. So, but there will be big
Actually,
changes.
I just think means I think more actually in my thoughts. So those question actually comes in my mind. That's just
That's certainly. I mean, yeah, that's true. That's certainly possible. I mean, if you change the Higgs field, everything's changed. So yeah.
okay.
So any other question? I don't see anything in the chat box.
Maybe no.
Yeah. Do you have a question?
No, I think there is no question. So,
Okay. Sorry, I thought there was questions. Okay. Okay.
So I think we can conclude.
Sorry, say it again.
So we can conclude our session.
Okay.
If you have any
sure.
suggestion, maybe if you have said previously that the student have to do something. So could you repeat that? Or for review or for something?
Sorry, I missed the last.
So do student need to do something after this?
Okay. No. Well, if they want to fill the survey, that they are. Otherwise, it's fine. If they don't, no, they don't have to do it.
Okay. So I think then we can conclude. So thanks again. This
Okay,
will be
thank you.
Your third time with us. So it's very great for us, and it's a great opportunity for our student to interact with you. Hopefully, we can arrange another this type of session with you. So bye for today. Thanks.
Yeah. That would be nice. No, thank you very much. Thank you.
See you.
Thank you, sir.
Bye bye.